Hello and greetings to everyone. My name is Lazaros Laskaridis, and today I will present you my work, which is the exploring dynamics of a cubic map incorporating a discrete memristor via microcontroller. This work has been done with my supervisor, Professor Christos Volos, and also Ioannis Toupoulos at the Laboratory of Nonlinear System, Circuits and Complexity, Department of Physics in Aristotle University of Thessaloniki. Before we start our presentation, we are going to see the outline of this work. So we are going to see what we are going to talk about. In the first part, we have the introduction, where we are going to present a little history about the Memristor. What is a Memristor? Second, we are going to see the model of the proposed discrete Memristor. And the third part of the introduction will be the cubic map with the proposed discrete memristor, how they are going to be combined. In the second part, where we are going to present the numerical results, we are going to present the dynamical behavior related to the parameter D and K, which is a parameter of the system. And in the final part, in the conclusion, we are going to talk about all the conclusions. Starting now from the introduction, in the first part, we see a memristor device here, and we are going to talk a little about this. A memristor, it is a nonlinear resistor with memory. This information was missing and found by Chua, and here this red arrows connects the flux and the charge. The memristor has a characteristic curve of the voltage and current. It is like an 8, and it is presented by this equation where the V is output voltage of the memristor, the I, it is the input current of the memristor, and the Q, it is the internal state of the memristor. Also, the M function here, it is called as the memriscence of the memristor. Now, we are going to talk about the model of the discrete memristor and how we are going to transform from the continuous to the discrete memristor by using the Euler difference method. The continuous equation 1 that we saw before now is discretized, and the ideal model of the discrete memristor, it is presented here by the equation 2. And now this ideal model of the discrete memristor, we are going to combine with the cubic map, where here the cubic map, it is presented in equation 3, where D is a parameter and Xn, it is the initial condition. So now we are combining the cubic map and the discrete memristor in one equation, and the final system that we are going to talk and to analyze, it is presented in equation 4, where now K, it is a coupling parameter, where in the first part of the equation 4 here, it is a cubic map, and we combine the cubic map with the discrete memristor, and now we are using the y square minus 1 function as a memriscence. But in order to verify that this memriscence, the y square minus 1, it is an appropriate memriscence, we have to give a current in the form of a sinus wave, and then to plot the characteristic curve for different frequencies. So in the left diagram, we see that for y0 equals to 0.01 coulomb and an amplitude about to 20 milliampere, we have the characteristic curve of the Memristor for 3 different frequencies, and we observe that as the frequency increases, going from the blue characteristic curve to green characteristic curve, the curve tends to be a straight line, and this confirms the characteristic curve of the Memristor. Also, in the right diagram, we present the characteristic curve of the Memristor with the voltage and the current. Now, for a specific value of the frequency, and especially equals to 0.06 rad per second, and now that we are chasing, it is the amplitude, where for 3 different values of the amplitude, for 5, 10, and 20 milliampere, we see that as the amplitude increases, also the characteristic curve increases too. Next, we have the experimental realization with the STM32H723 microcontroller. This microcontroller has an ARM CPU at 550 MHz. It has also 564 kilobytes of RAM. Also, we have one DAC of 12 bits and with 2 channels. And we have connected this microcontroller with the computer and the oscilloscope, and we're passing the data through DMA, which is the direct memory access. Now, we're going to see the experimental results. We are presenting the bifurcation diagrams with the parameter D for k equals to 1.6, and also the initial conditions are the same for all cases. They are equal, the x0 equals to 0.1 and the y0 equals to 0.01. Here, from the bifurcation diagram, we observe that the system starts from a fixed point, then goes to period 2, then also the system presents quasi-periodic behavior here, and then goes to period 6, and then through periodic phenomena, it is going to house. This behavior it is confirmed and from the Lyapunov spectrum in the right diagram. And here we are presenting the results from the oscilloscope. Next, we are going to see some cases. For d equals to 0.3, there is one fixed point. Then increasing the d, we are going to period 2. For d equals to 1.3, we are going to period 6. And now by increasing the parameter d, we are seeing that we have a quasi-periodic behavior here. And in the last 2 cases, for 1.4 and 1.5, we have 2 chaotic attractors with the first Lyapunov exponent to be positive and the second one to be negative. Next, we are taking again the bifurcation diagram, but now for the value of the parameter k equals to 1.8. And now we see the difference from the previous. It is that the system starts again from a fixed point. Now it ends to a fixed point, and also we are not having no quasi-periodic behavior here. So again, we are presenting the Lyapunov spectrum and also now the numerical results from the oscilloscope. And now we are presenting 2 cases where for d equals to 1.15 and for d equals to 1.5, we have one chaotic attractor and one hyper-chaotic attractor. And we see that we have 2 positive Lyapunov exponents, and the results are presented here and from the oscilloscope and the Lyapunov exponents at the right diagram. And now we are changing the bifurcation parameter. Now the bifurcation parameter, it is k, and we are starting for d equals to 1.3. Now we see that the system goes from 0.6 until 2, and also again we have like the same behavior as in the first bifurcation diagram. And here we have also quasi-periodic behavior. We see that for k equals to 1.54, it is quasi-periodic behavior, and for 1.8, it is chaotic attractor, and for 2 equals to 0, it is an hyperchaotic attractor. Next, we are presenting the bifurcation diagram for D equals to 1.6. Here we see, except from the higher quasi-periodic behavior, we have and periodic windows inside the chaotic regions, and the system goes to house with periodic behavior. Here in the right diagram, we present a focus region of this bifurcation diagram that captured from the oscilloscope. And also here, again, we are presenting one chaotic attractor and one hyperchaotic attractor for two different values of the parameter k, 1.6 and 1.7. And finally, we are presenting a bifurcation diagram for the value of the d equals to 1.8. Again, we are presenting the focus region in order to be more clear, and we are seeing that here we are going to house through periodic phenomena. This is the focus region, and finally the system goes to a fixed point. So again, here we are seeing for this value of k, period 12 attractor, and we presenting one chaotic attractor again and one hyperchaotic attractor. And finally, we saw the experimental implementation through the microcontroller. Also, we saw how through the period W phenomena and quasi-periodic behavior, hyperchaotic attractor occurred for different values of the parameter D and K, and dynamical behavior of the system started from on period 1 or fixed point and ended to a fixed point for specific cases of the parameter D and K, and for K equals 1.6 and for values of the parameter D lower than 1.6, no hyperchaotic attractor was occurred. This was my presentation. Thank you for your attention, and if you have any questions, you can send me to this contact email. Again, thank you for your attention.